All right, I'm back for part two of our exam review, test review, whatever you want to call it. So we did our graphing earlier. Now we're going to take a look at our inverse functions, and we'll just take a look at one application because we've kind of done a lot of those applications in the past. So let's go right back into our MyMathLab, and I've skipped forward to number 25 here. So again, not covering every problem, so hopefully you'll be able to go through and do the in-between problems, either based on this video, previous work, or just looking up facts from your notes, excuse me, from your notes or your textbook. But this graph here, I'm so used to saying graphs because I just finished doing that, so not a graph, but in this inverse function here, remember that we basically talked about inverse functions before. Right? So we can talk about the idea that this is an inverse function, but what we're really asking here is what do I take cosine of that gives me negative square root of 3 over 2? Okay, and so that's the main idea, but now that we've talked about, I guess not we, but you've read about your inverse functions um, from section 2.3, you'll realize that in the definitions, we have to worry about quadrants now. When we first talked about inverse functions, everything was in quadrant 1, and so we didn't have to worry about it. We would just say, well, what is our memorized value that gives us what we want? At that point, we had just had values in quadrant 1, so there was no issue here. But now that we're working in a bigger picture, we have to realize that there are a whole lot of different angles that I can take cosine of to get negative square root of 3 over 2. So we need to make sure that we pay attention to our definition of the inverse cosine. So not only are we looking for an angle where we end up with a cosine of that angle, why isn't it typing for me? Cosine of that angle should be equal to negative square root of 3 over 2. Okay, so that's what we first started with, but we also have to know our rule or our definition of inverse cosine. Inverse cosine will take a positive number and put it in quadrant 1. Okay, so when we're working with any of the inverse functions, a positive number will always go into quadrant 1. It's the negative numbers that we have to be careful with. So just look back in the textbook in your notes for the definition, and we're looking at an angle in quadrant 2 when we're working with inverse cosine. Okay, that's the one that's different. Inverse sine, inverse cosine, they both go down into quadrant 4, and you're actually working with negative angles when you're in quadrant 4 when you're working with inverse functions. But inverse cosine goes into quadrant 2, where things would naturally be working with positive numbers or positive angles at least, but we need to make sure that we're in quadrant 2. Okay, so the way that we've done this in the past, though, is we didn't really say, well, let's think about the angles in quadrant 2 and pick out which one gives us negative square root of 3 over 2. What we did is just ask ourselves the same question that we've had earlier, where I'm taking cosine of something to get negative square root of 3 over 2. But to find that, we don't solve for theta, we solve for its reference angle. So we want to know what the reference angle is by finding cosine of the reference angle would be equal to not the whole negative square root of 3 over 2, just the square root of 3 over 2. So remember our definition of the reference angle is the angle in quadrant 1 that matches up with the angle between the x-axis and the actual angle in whatever quadrant it's in. So if we figure out what the reference angle is, we can very easily figure out what the angle we're looking for in quadrant 2 by using our reference angle properties. Okay, so this is nothing more than memorization. If we're looking for cosine of the reference angle being square root of 3 over 2, we know then that the reference angle would have to be, keep in mind that we're in radians here, excuse me, and not degrees, but we're looking at in radians, theta prime is equal to pi over 6. Okay, so what that tells us is that our angle in quadrant 2 is pi over 6 units away from the x-axis. So in quadrant 2, our actual angle is going to be a little bit less than the x-axis. So in quadrant 2, the closest x-axis is the negative x-axis. The negative x-axis is pi radians. We're a little bit short of that, so we have to subtract away that reference angle. And when we do that subtraction, hopefully you've done this a million times so you don't have to write this out, but you get a common denominator by putting pi as 6 over 6, and you do your subtraction, and you're going to be left with 5 pi over 6. And so you don't always have to find reference angles. Some of these are easier than others, but I would encourage you, especially with cosine, to kind of think through it this way. You can do the same thing with sine and tangent, but those have different patterns that make things just a little bit easier to deal with. Right, so again, let's just go back into MyMathLab, put it in there, and make sure that we have the correct answer and that I didn't make any mistakes before we move forward. But we ended up with 5 pi over 6. I do not know why it didn't turn into a pi there. So I guess I'll push the pi symbol, check our answer, and we're perfect. Okay. So more or less, the next few problems are more the same thing, kind of over and over and over here. So I actually do want to do not this one. Let's get one more forward here. We're going to do one where we have an inverse cosine kind of bridged together with a regular cosine. So I went through and decided to do this one because we've just done a cosine problem. So I wanted to make sure that we did another one to tie in exactly with what we were doing here. So kind of scrolling down, we just dealt with cosine inverse of an actual number here. Now we're dealing with cosine inverse of another expression. Okay, so again, there's other ways of doing it, but you don't have, so you don't have to do it this way. But I'd rather just mimic the same process over and over and over. We just got done saying that it does depend on, excuse me, our quadrant depends on the sign of what's going on in here. So we have to break this down a little bit. I don't want to write everything out here, but breaking it down, this 8 pi over 9 right there, what quadrant's that in? And it's certainly more than pi over 2, so we're not in quadrant 1, but it's certainly less than pi. So this angle itself is in quadrant 2, and we know that cosine in quadrant 2 is negative. Okay, and so maybe I'll write that out just to make sure that we're clear about that. That if we're working with cosine of 8 pi over 9, whoops, we know that that is negative, since that 8 pi, darn it, did it again, over 9 is in quadrant 2. Okay, so we had to think through that for a second so that we knew that we were taking the inverse cosine of a negative number. That does force us once again to be in quadrant 2, just like we talked about before. And now this is the part that's going to look a little bit weird, but, oh, sorry, I got stuck in there. And kind of do some copying pasting again to fix that. So this time around, we're looking for something where this is the inverse function. We're looking for theta, so that cosine of theta is equal to whatever this value in here is. So let me scroll up so you can see this. So just to compare and contrast here we said that our inverse cosine is going to give us an angle theta, where cosine of theta was equal to whatever the number was inside here. So down below, same thing. The inverse cosine is going to give us the value theta, where cosine of theta is equal to whatever's on the inside. And I don't know what cosine of 8 pi over 9 is, so we'll just leave that as cosine of 8 pi over 9. Okay, so if you write it this way, in certain problems at least, this becomes kind of a no-brainer. Okay, so we're looking at this and saying, I'm looking for the angle in quadrant 2, so that cosine of theta is equal to cosine of 8 pi over 9. But we just got done below here saying that 8 pi over 9 is in quadrant 2. And so, of course, if I replace theta with 8 pi over 9, I'm going to get a relationship that's 100% equal here. Okay, so there's not really anything else to write here. I guess I'll make it as clear as I can. But theta has to be equal to 8 pi over 9. Right? So just talking through it one last time, cosine of 8 pi over 9 is negative because 8 pi over 9 is in quadrant 2. That's how we knew that we needed our angle to be in quadrant 2, because the inverse cosine of a negative number is in quadrant 2. Then we say the inverse function gives us the angle theta such that cosine of theta is equal to whatever we're taking the inverse of. And so we get this relationship. And be careful here, because there's more going on. You can't just say, well, let's ignore the cosines and we get theta is equal to 8 pi over 9. But that works in this case because we know that we're in quadrant 2 and 8 pi over 9 is already in quadrant 2. So you can see down below, we're going to have a very similar question with tangent. We'll talk about it in a little bit more detail. But for now, 8 pi over 9 is the answer that we're looking for. So let's, again, double check and throw it in here and make sure that there's no issue. But check 8 pi over 9 and tells us we're good. Right, so moving on to number 28. You'll see this is the exact problem that I'd copied in Word, so we'll just go right back over there. And so this one's a little bit different. We still have to break this down. I'm not going to write quite as much because I'm going to have more to talk about here, but we can think through this. 5 pi over 3 is pretty close to 2 pi, so that's going to put us in quadrant 4. In quadrant 4, tangent is negative. So we need to know from our facts, what does inverse tangent do to a negative number? Well, inverse tangent for negative numbers are going to go into quadrant 4, but we have to be careful there. So they are going into quadrant 4, but we need to make sure that as we do that, that our angle is negative. Right? We're not looking for something like 11 pi over 6 or 7 pi over 4 or 5 pi over 3. We're looking for a negative angle in quadrant 4. And along with that, we still need to have the same relationship we had up above. That tangent inverse is going to give us an angle theta, and when we take tangent of that angle theta, we better get whatever we have inside the parentheses. So we're looking at tangent of 5 pi over 3. Okay, so just a quick compare and contrast here with the problem up above. Up here, we can kind of just solve this by ignoring the cosines because we already knew that theta was supposed to be in quadrant 2. 8 pi over 9 was in quadrant 2, so we are good. Okay, this time around, if I try to drop the tangents, I'm halfway okay, but not fully okay. If I just drop the tangents, I'd get theta is equal to 5 pi over 3, which is in quadrant 4, but it's not negative. Okay, and so that is not going to be the answer that we can do this time. Right, so there's two different ways of handling this. One is just to move it into the correct, I shouldn't say correct quadrant, it's already in the correct quadrant. We just need a negative angle. Okay, and so if I'm looking for a negative angle, one way of doing this is just to use, oh my goodness, my mind went blank, coterminal angles that have the same ending point but differ by full rotations. So what we're really looking at, if we take it in that perspective, is that we're starting with 5 pi over 3 because we know that that's the angle in quadrant 4 that works for us. We just need it to be negative. So let's subtract away one full rotation here, and again, get common denominators as necessary. But if you take 5 pi over 3 and subtract away a full rotation, you're going to end up with negative pi over 3. And I apologize again for the pi not showing up the way that I thought it would. Let me fix that so it looks nicer in the video. But that's kind of the fastest way to do it. You know, if you know that you have the right angle, but you're missing the sign, or even if you have an angle that's in the wrong quadrant, you can kind of just do arithmetic either with coterminal angles or with, excuse me, reference angles in order to make that work out. Now, on the other hand, because 5 pi over 3 is something that we are familiar with, we could break this down another way. You don't have to do it this way, but you can also, my goodness, just trying to space this out a little bit. You can also actually just evaluate 5 pi over 3. So let's just put in our tangent of theta again. This doesn't always work because you don't always have memorized values like this. But we already talked about this being in quadrant 4 where tangent is negative, so we have a negative sign there. The reference angle is just pi over 3. Remember, our shortcut for radians, just take the coefficient off the pi. So our reference angle is pi over 3, and tangent of pi over 3 is the square root of 3. And then finally, if you're looking at that, you can take this a step forward then and say, well, if tangent of theta is negative square root of 3, we can go through and do our reference angle thing. So we're actually looking for tangent of theta prime being equal to square root of 3, which would tell you that theta prime, surprise, is equal to pi over 3. Because if I take tangent of pi over 3, that's what gives me square root of 3. It's kind of reversing what we just did. Now we need to make sure that theta has that reference angle in quadrant 4. And so I guess maybe I wish I would have drawn a picture here, but I don't have one, so I apologize. But all we're doing here is saying, well, if I need to be in quadrant 4 with a negative number, if I just put a negative sign in front of that, that's certainly going to put me down into quadrant 4 instead of quadrant 1, and pi over 3 is certainly not large enough to push me down away from quadrant 4. And so that's really just telling you then that theta has to be negative pi over 3. And of course, that's the exact same answer we had up above, just a different way of doing it. Okay, so again, that finishes that particular problem. So we'll go back into MyMathLab, double check that we did it correctly. But notice here, in case it wasn't completely clear earlier, that sometimes you do get the exact same angle that you started with, other times you don't. It absolutely depends on the function that you're working with, the number that's in here, because the different inverse functions have different definitions for their domain and range. Okay, but that is the final answer here. Okay, so I feel like maybe I should go back into Word and talk just a, whoops, that's not what I wanted to do. Talk about this just a little bit more. So let's do another problem here. I'm going to do some copying and pasting. So this is a little bit off the cuff. I apologize if this doesn't go well, but I want to do another problem very similar to number 28. Let's just keep the tangent here. But let's say that we're working with something just a little bit weirder. Maybe we're working with a 2 pi over, no, let's do a 3 pi over 5. Okay, so instead of 5 pi over 3, we have 3 pi over 5. Okay, so of course that changes this over here as well, but there's a little bit more going on here. So this time around, we have to make sure that we are still working with a negative value to make sure that we are still in quadrant 4. So 3 pi over 5, 3 over 5 is just a little bit more than 1/2, so just a little bit past pi over 2, which puts us in quadrant 2. So in quadrant 2, tangent is negative, and the inverse tangent is still going to go into quadrant 4 where theta is negative. So I kind of changed this a little bit so I didn't have to deal with changing too much of the problem. Okay, so now the main difference is we cannot use coterminal angles, right? Because this is in quadrant 2. If I just try to subtract away 2 pi here, it's just going to put me in another quadrant, sorry, a negative angle that's in quadrant 2. Or if I add, 2 pi to it, it's still going to be in quadrant 2. So unlike this one up like here, where it was in the correct quadrant, but the sign was wrong, this one is in the wrong quadrant. Okay, so the idea is that we can kind of fix that using reference angles more than anything else. So like I said before, you can't just ignore the tangents, but at the same time, we don't want to have to get a calculator out and take tangent of 3 pi over 5, get some sort of crazy answer here. But we do know that if these two things are equal, then the reference angle of theta needs to be equal to the reference angle of 3 pi over 5. So we're going to start with that here. So the reference angle, not the angle itself, the angle doesn't have to be 3 pi over 5, but the reference angle has to match the reference angle for 3 pi over 5. Okay, so I hope that makes sense. Two angles don't have to be the same if they have the same tangent or same trig function, but because of our properties of reference angles, they do have to have matching reference angles. And then the reference angle with 3 pi over 5, we kind of talked about this previously in quadrant 2. We're measuring the distance away from the negative x-axis. So we're taking pi and subtracting away 3 pi over 5. And again, get common denominators as needed, but the reference angle ends up being 2 pi over 5. Okay, so now what we need then is our angle theta is negative in quadrant 4, and we know that its reference angle is equal to 2 pi over 5. Okay, but now that I have that reference angle, you can kind of see that it matches up with what we've done before here. Because we're working with negative angles in quadrant 4, a reference angle is guaranteed to be in quadrant 1. Yeah, that's just the definition of what a reference angle is. If you make an angle in quadrant 1 negative, it's absolutely going to stick it into quadrant 4. Okay, so the final answer here with that last step then is simply that theta is equal to negative 2 pi over 5. And again, I just made that problem up. It's not in MyMathLab, so there's nowhere for me to go type that in. But that would be the final answer for this particular problem. So very similar ideas, and that's not what I'm trying to do either. Just trying, there we go. Just trying to highlight that so it's clear later on if you look through the video that this is the answer. So you can still, anytime you're working with repetitive inverses here, there is some sort of relationship so that you don't actually have to go through and calculate values or use a calculator. It's just a matter of talking through and thinking about the problem and realizing that, hey, either we have the the angle that's in the right quadrant but the wrong sign, or down here we had the angle that's in the wrong quadrants. We need to fix it and put it in the correct quadrant, make sure the sign's correct. Or maybe we even have a problem where we didn't have to do anything. It was already the correct sign and the correct quadrant. So it's really just a play on making sure that you're working with the definitions and using quadrants correctly. Right, so that was our last problem where we were working with just straight a tangent inverse of tangent or cosine inverse of cosine, so on and so forth. The more important problem in a calculus sort of class is making sure that we can address working with cosine of sine inverse or maybe sine of sine inverse, so on and so forth. Right, so this one, there's not too much work to show here because it's kind of leading you through the problem, but we're going to have the same setup as we have done before. So I guess maybe I should type up a little bit here. So I apologize that I didn't get this in Word immediately, but we go back into the Word document. We're just going to have a little bit more room than what I had originally planned here. So let me do some shifting around and hopefully we can fit this all in here. But what we're looking at is, now I have to go back to the problem, so I'm not sharing the screen, I'm just looking the problem back up again. So cosine of sine inverse of negative 4/5. Okay, so I'm going to peek one last time, make sure that that's absolutely correct. It is. All right, so goodness, got to get back to it now. That's not right either. All right, I'm going to stop the share so I can see what I'm doing here. Sorry about that. So you can tell I'm completely new at this, and I apologize for the confusion there. Okay, but now back to where we were at. This is something that we can kind of set up the same way that we are doing here. So we're just going to make a quick substitution. Anytime we're working with an inverse function, we want to realize that that gives us an angle. So if I replace sine inverse with the angle theta, that tells us we're looking for cosine of theta when, I can write this out in two ways. I'll start with this, but when theta, my goodness, is equal to sine inverse of negative 4/5. Okay, so if I do it like that, that doesn't really look like it helps all that much because I'm still dealing with sine inverse of an angle that I don't actually know. But we can take that one step further and say that we're working with cosine of theta when, and now let's just turn this around the way we have been. If theta is equal to the inverse sine, that means if I take sine of theta, I should get negative 4/5. Okay. But remember that our definitions of working with our inverse trig functions forces inverse sine of a negative number to go into quadrant 4. Okay. So here, because we're not actually solving for an angle, we don't have to worry about the fact that theta should be negative. But this portion right here, finding cosine when we know the value of sine, that's something that we've done since section 1.2, if I remember right. It's been a couple of chapters, but we can go through here and just use the definition of sine to draw our right triangle in the correct quadrant. It needs to be in quadrant 4. Once we have that right triangle drawn in, it's just a matter of using Pythagorean's theorem to find the missing side and then use that to find cosine of theta. So let's go back into the problem itself, because it actually had a picture drawn, which is why I didn't have it prepped in my Word document. But here it's asking, hey, what's the triangle that you would draw? Notice every single one of these triangles is a quadrant 4, exactly the way that we had talked about. And now it's just a matter of remembering where these numbers go when we're dealing with sine. Okay, so sine of theta was equal to the opposite over the hypotenuse. So we know the hypotenuse needs to be 5, so it's either choice A or choice C. And the side opposite of theta is supposed to be the numerator, so we get y equals -4 here, not x is equal to 4. So this is the setup of our picture. Just double check that. And now it's just a matter of saying, well, let's use Pythagorean's theorem. So I don't even know if I need to type anything on the other page. I'll go ahead and do it, but I use Pythagorean's theorem. I get x squared plus -4 squared is equal to 5 squared. And that's a very easy Pythagorean theorem to solve. Right? But again, if you don't remember your Pythagorean triples, it's a little bit trickier, but all we're doing at this point from the diagram is saying that we know the values of the hypotenuse on one side. We don't know what x is, but x squared plus that -4 squared needs to give us 5 squared. And from there, just watch your signs. Squaring a negative turns it positive. Squaring the 5 gives you 25. That leaves you with x squared when you subtract 16 from both sides is equal to 9. And really the only reason I was writing this out is to make sure that, remember, when we take the square root of both sides, you get both a plus or minus square root. So remember, that doesn't mean we have two different answers here, it just means that we have to decide. So in quadrant 4, is x positive or negative? That's positive because quadrant 4 is on the positive side of the y-axis. So you are going to get x is equal to positive 3 here. Right, so just kind of keep that in mind, that x is equal to positive 3. And then going back to our MyMathLab, so we can take a look at the picture, we know now that we're working with this where x is equal to 3. So finally, we're done with this. This just represents this whole sine inverse of -4 over 5 represents this angle theta here. So all we're saying is, hey, what's cosine based on this triangle? Well, cosine is adjacent over hypotenuse. We just found the adjacent side to be 3, and the hypotenuse is still 5. And that's that. Right? So it's kind of the problems we've done in the past in disguise, where we have to use properties to know that we need to be in quadrant 4, so on and so forth. But once we know we're in quadrant 4, just draw the triangle, use Pythagorean's theorem to figure out that x has to be 3, and then cosine would be adjacent over hypotenuse. Right? So that's version 1 of that type of setup. The second version is exactly the same idea. It's just we have a variable in here instead of a number. Okay, so this type of problem comes up a little bit more often than you would think in a calculus class. So just make sure you read the entire instructions. I know I'm bad at that, especially when I'm going over quick examples here, but it blatantly tells us here that x has to be positive. So if x is positive, that means we're absolutely working in quadrant 1 here, so that at least helps us out. Right, so again, go back into my Word document so I can do a little bit of typing. But we just said that x is positive, so that means that we are working in quadrant 1. And we're, once again, kind of breaking this out. We're looking to find what tangent is when cosine theta is equal to x. Okay, so I guess one thing to kind of mention here, we're about to draw a picture in quadrant 1. I guess I can unhide it now. We know that we're supposed to be in quadrant 1, so we're drawing a right triangle in quadrant 1. We need to use this fact that cosine of theta is equal to x to draw in some information into our right triangle and be able to solve for the missing side. And so one thing to be aware of, if cosine is defined to be a fraction, so you do probably want to rewrite the fraction as the whole number over 1, just so that becomes a little bit easier to view. And so cosine tells us that the x value, the opposite side of that angle, I have to be careful here. When I say x value, I mean the horizontal value in our graph, is actually x, the number that we don't know there. Okay, and then the denominator is the hypotenuse. Okay, so we would label the hypotenuse with a 1 there. And then finally, we don't know the y value moving up or down there. Okay, so this is something where you're going to have to be careful with your Pythagorean theorem. You know, we have a bunch of x's here, we have a bunch of x's here. We want our answer to be in terms of x. And so please, when you are working with the Pythagorean theorem here, don't solve for x so that things are now all of a sudden written in terms of y. We absolutely need to make sure that we're solving that triangle for y. Okay, otherwise, we're going to get a bunch of y's in our answer that don't match up the initial x's that we started with. And so this is, again, just Pythagorean's theorem. We know that if I square the two shorter sides, so if I square x squared and add on the square of y, that should give you 1 squared. And of course, I'm not going to rewrite the whole thing just to square the 1, but 1 squared is 1. If we're solving for y, we'd want to subtract the x squared from both sides, so y squared is equal to 1 minus x squared. And then finally, we do need to take the square roots, but remember, when we take the square root, we still get that plus or minus out in front. So I'm always emphasizing that just so things go easier in chapter 3. That's technically what's happening here, but remember, we're in quadrant 1. In quadrant 1, everything is nice and positive, so even though we think about that for a split second, we don't need it, right? We know it's positive, so we end up with y is equal to the square root of 1 minus x squared. And so I'll go ahead and make this text box just a little bit bigger so I can actually fit that in there. But y then is the same thing as square root of 1 minus x squared. Didn't quite make that big enough. Okay. And then finally, it's just a matter of saying, well, this is the triangle we get based on cosine inverse of x. Now we need to take tangent using this right triangle. So I didn't label it, but theta, of course, is kind of right there based on what we've been doing. So we know that our answer, just like we've kind of spelled out here, our answer is equal to tangent of theta. Right? We're trying to find tangent of theta when cosine was equal to x over 1. That's giving us the answer there. And tangent theta is nothing more than the opposite side, which would be the square root of 1 minus x squared. Right? The side opposite theta there. And we're dividing that by the adjacent side, which is just x. And so you oftentimes get these scary looking expressions here, but it's nothing more than using Pythagorean's theorem with a handful of variables as opposed to just working with numbers. And then remembering your definition for tangent. Okay, so that's it. We'll go back into our MyMathLab, make sure, again, that I didn't screw up. It's one nice thing of doing it this way. It's making sure that I have the correct answer. But we end up this time, have to do a little bit more typing. We have a fraction, we have a square root in our fraction, we have a 1 minus x squared in the numerator, and an x in the denominator. Double check that, and it tells us we're awesome. Okay, so just to throw this out here, in calculus, we do this a lot just because if we're working with a tangent of cosine inverse, that's a pretty complicated relationship to be working with. Whereas if we write this as a square root divided by a variable, I know it's not the easiest, but working square roots is a little bit easier than working with an inverse function. Right, so that's why that comes up later on. Right, so that finishes all the inverse stuff we needed to talk about. It's basically just know your inverse facts, be able to take the inverse of any sort of angle, and then be able to work with these weird compositions of the inverse functions. Right, so the last example we're going to do, we're going to skip some of the applications because they're all the same. It's all just based on can you draw or can you recognize the right triangles. So here you can read through this, but you've got a hot air balloon going straight up in the air. At one point, you look over and it's making an 18.9 degree angle with the ground. A few moments later, you look over and see that it's up at 32.5 degree angle. And we're just asked how far did it rise from those 2 points. Well, just looking at this, you can see that this is really just two right triangles put together. And so don't try to do this all at once. Just try to go ahead and separate those two right triangles and see what you can do here. Right? So here, this is just my crude relationship. I took this without all of the pictures and diagrams and stuff and just said, well, hey, there's the basic essence of what's happening. There's a right angle that I didn't bother to draw in here, but that separates and kind of matches up here. So all we're saying is take this larger angle as one right angle, where we know the larger angle has a 32.5 degree angle here. We know that the base is 100, and I mistyped that. The base is 121 feet along the bottom. I guess it's going to happen twice. But we don't know how high it went or high it is. And the same thing's going on here. We're looking at this bottom right triangle this time. This one only has an 18.9 degree angle. And again, we know how the horizontal distance is, but we don't know its vertical distance. And just comparing and contrasting, the distance we're looking for is exactly the difference between these two heights. So all we have to do here is use our trig functions and notice that we're working with the opposite side and the adjacent side. Opposite and adjacent means we're working with tangent. So this tells us that tangent of 32.5 degrees has to be equal to h over 121. Okay. And as we've done a bunch in the past, now it's just a matter of multiplying both sides by 121 to solve that for h. And we'll just let that go for now. We'll use a calculator to come up with our estimate, but that's the exact value of h. Okay. And the other triangle, where we've got basically the exact same thing going on. And it's still opposite over adjacent, so we're still working with tangent. Now instead of 32.5 degrees, we're working with 18.9 degrees. And we just use a different variable here. The names of the variables don't matter. Just make sure that they're different so you can keep track of what's what. But otherwise, it's exactly the same. And once again, all you're doing to come up with the value of y is multiply both sides by the denominator, and that gives you a value of y. Right. So finally, our answer is just subtracting these two values. So I'm going to go ahead and type it up here, but we're going to put this in a calculator in just a moment. But we take our first expression, bump something there, and subtract away our second expression. I can't type again. Sorry about that. Go away. It's 18.9 degrees. Okay. So now it's just a calculator problem. I almost hesitate to bring this up, but you definitely don't want to do this one part at a time. Just type this whole thing into your calculator. So I'm just doing this to make sure it's clear that you should be using a calculator to do this all at once now. Don't need that. But we had 121 times tangent of 32.5, and then subtracting away 121 times tangent of, I believe it was 18.9, yeah. And then I don't want to be too confusing, so I'm not going to hit enter, but what do we have to be careful with our graphing calculator? Always have to make sure that we're in the right mode. And so previously, when we were doing graphing or other ideas with your inverse functions, maybe you were in radians. This is definitely in degrees, so before you hit enter, go in here, make sure it's in degrees. If it's not, just switch it over to degrees, exit out, go ahead and hit enter, and it pops up and it gives you 35.6579. Going back to the problem, we'll see this in a second. It said round to the nearest tenth. So that 5 makes us round up, and so we're going to get something that's about 35.7. And that is a distance, and everything else was measured in feet. So that's also going to be measured in feet. And I'm going to double check that, sorry, I think I forgot to switch over to my Word file here. Other than just double checking that I remembered that correctly, that is exactly what we're doing for an answer. So we should end up with 35.7. Go back into MyMathLab, throw in the 35.7, and hopefully, again, I didn't make any silly mistakes along the way, and we're good. All right, so of course, that's not all of the problems that you have to work through, but hopefully that gives you a good understanding of a lot of the different types of problems that you'll encounter. So again, remember, if you have any concerns or questions about anything as you go through the test, please shoot me an email and ask. I haven't had too many, so I'm hoping that everybody's in relatively good shape. But if you've just been confused and maybe scared to send me an email, don't. I'm kind of sitting around waiting for emails and responses. So let me know if you have any problems. Good luck studying, and have a great day. Bye.